Hello everyone. Today's topic is Booth's multiplication algorithm. This is a multiplication algorithm. This allows two signed binary integers in a 2's complement form. It performs multiplication of two numbers with the help of 2's complement method. So first of all, what is meant by 2's complement method? 2's complement method means if any number we have in binary form, first we have to convert that form into 1's complement. How to convert it into 1's complement means, so all the zeros are changed to 1, all the ones are changed to zeros. In the 1's complement method, zeros are converted to 1, ones are converted to zeros. That is the 1's complement method. In the 2's complement method, we are adding 1 to 1's complement method, we get the 2's complement value. So here in the Booth's multiplication algorithm, we are performing multiplying two values with the help of 2's complement method. Those numbers are signed binary integers. So Booth's multiplication algorithm is a multiplication algorithm. It allows us to multiply the two signed binary integers in 2's complement method. So what is the use of this Booth's multiplication algorithm means? It is also used to speed up the performance of the multiplication process, and it is very efficient. How it works means, it works on the string bits zeros in the multiplier that requires number of additional bits only shifting to the rightmost string bit, and string bit of ones in a multiplier bit weight 2 power k to 2 power m, that can be considered as 2 power k plus 1 minus 2 power m. Now see the flowchart for Booth's multiplication algorithm. This is a pictorial representation for Booth's multiplication algorithm. First we start the procedure. So next one is initialization. It is the initialization of a variables in a multiplication algorithm. So here first one is accumulator. AC is indicated with accumulator. Accumulator is assigned with 0, and initially we are taking Qn plus 1. Qn plus 1 is also 0, and it is a sequence counter. SE is used for sequence counter, which is used to count the number of times loop can be repeated. So we are taking the number of bits in the multiplicand. So total number of bits in the multiplicand or multiplier that can be assigned as sequence counter value. So n indicates number of bits. The total number of, for example, multiplier contains 4 bits, 0 1 0 1. So 4 bits we have in the multiplier. So sequence counter is initialized with n value, that is 4. N means total number of bits available in the multiplier. So initially we are taking the values are accumulator, Qn plus 1, sequence counter, and we are assigning two values. Those are B register or BR register in multiplicand, QR register is stored in the multiplier. Multiplicand and multipliers are stored in the B register and Q register. Okay, this is the initialization step. After initialization, we have to compare the values of Qn and Qn plus 1 value. Initially, we are taking the Qn plus 1 is 0, and Qn, that means least significant bit of Qn and Qn plus 1 will be compared. Least significant bit of Qn value and Qn plus 1 value will be compared. Here we are getting 4 chances. What are the 4 chances means? If both are equal, that means 0 0 or 1 1. Or we get 0 or 1. Qn is 0, Qn plus 1 is 1. Same way, Qn is 1, Qn plus 1 is 0. So these are the 4 possible conditions we obtain in the comparing of Qn and Qn plus 1. So if both are 0 0 or 1 1, simply we are performing the arithmetical shift right. Whatever the accumulator value is there, that can be shifted to QR, and QR is shifted to Qn plus 1 position. Okay, after that we are decrementing the value of sequence counter value. Initially the total number of bits available in the multiplier can be taken as sequence counter value, and we are decrementing the, after performing arithmetical shift right, we are decrementing the value. Next, if there is a chance to get 1 0, Qn is 1, Qn plus 1 is 0. So if there is a chance to get qn plus 1 is 1 0. Now what the operation we are performing is, we are adding the accumulator value, whatever the P4 value there in the accumulator, that can be added to the 2's complement of multiplicand value. That is B register value, we are complementing the value, plus we are adding this value to 1 BR register. So we get the 2's complement value of multiplicand value. If there is a chance to get Qn value is 0, Qn plus 1 is 1. So we are simply add the accumulator value and B register value. And again, we after performing these two operations, we shift the arithmetical shift the operation, and we can decrement the counter value. So next step is, we are comparing the counter value. That means sequence counter value we are comparing here. If the sequence counter value is 0, we are ending the process. Otherwise, we go back to comparison of third step. That means Qn and Qn plus 1. After shifting the values of accumulator and QR value, then Qn value, least significant bit value Qn will be changed. So again we are comparing this value until sequence counter will be 0. Okay, this is the process or Booth's multiplication algorithm. Booth's multiplication algorithm, we are multiplying 7 into 3 by using Booth's multiplication algorithm. So initially we are taking the 7 value and 3 value in the binary form. So the binary form of 7 is 0 triple 1. If 7 is a positive value, that's why we are taking sign bit as 0, and 3 is a positive value again, so we are taking 0 as the sign bit value, and the remaining 3 bits indicates 3. Okay, now 7 is set in the M field and 3 is set in the Q field. This is the M is for multiplier, multiplicand, Q is for multiplier. Okay, these, and now the sequence counter is initialized with 4 values. Why? Because multiplier contains 4 bits. That's why sequence counter is assigned with 4 values. That is the total number of bits are 4. That's why sequence counter is assigned with 4. Okay, every time we are performing the comparing the values of q and qn minus 1, if it is there is a chance to get 0 0 0 1 1 1 1 0. So after performing arithmetical shift right, we are decrementing the counter value. If the counter value is 0, we are ending the process. Otherwise, we repeat the process. Now what is the process we are doing? You can see here. Now see here how to perform 7 into 3 by using Booth's multiplication algorithm. So 7 is stored in the BR register and 3 is stored in the QR register. So sometimes we are BR register we are also called as M. Okay, now see here. So 7 binary equivalent value is 1 1 1. So the sign of the 7 is 0. So Booth's multiplication algorithm performs two signed values. That's why we are taking sign bit is 0. And 3 is 0 0. 3 binary equivalent value is 0 1 1. So sign value for 3 is 0. So M register, BR register is stored in the 7 and QR register is stored in 3. Okay. So initially we have M equal to 0 triple 1, M complement plus 1 equal to 1 0 0 1, and it is M is also called as BR register. Q is nothing but QR register, and we are taking Qn plus 1. Qn plus 1 is initialized with 0. This is the initialization operations. So now coming to step 1. First step 1, accumulator value equal to, accumulator is assigned with 4 zeros. So total number of bits are 4. That's why we are assigning accumulator as 0, 4 zeros. Next one, Q value, Q is 0 0 1 1, and next one, Qn minus 1 or Qn plus 1, both are equivalent. So Qn plus 1 is 0 and sequence counter, so sequence counter is 4. So first what is the first operation means, we have to compare the Q and Qn plus 1 value. That means least significant bit of Q and Qn plus 1 value. If both are 1 0, so 1 0 means what are the operation we are performing? Accumulator value equal to 1 0 means, so Qn is Q and Qn minus 1 or Qn plus 1 is 1 0. 1 0 means we are performing accumulator value AC equal to accumulator value plus M complement plus 1. So initial accumulator value is 4 zeros. That's why we are adding this value to m complement plus 1. So we get 1 0 0 1. Next one 0 0 1 1 0. Sequence counter is 4. So this is the first operation. Second operation is arithmetical shift right. So now we are shifting the values. So arithmetical shift right means first whatever the value in the accumulator value, that means most significant bit value, you can write twice. So most significant bit value, write twice. So double one, and second position value is moved to third position, and fourth position is moved to third position value is moved to fourth position, and this one value is moved to Q. So this one value is moved to Q. Next one 0 0 1, and this value is shifted to Qn plus 1. Qn plus 1. So sequence counter is 4. After performing arithmetical shift right, third step is step 3 is decrement the sequence counter value. So the sequence counter already 4 is there. We can decrement the value. That means 4 minus 1. So the value is 3. 1 1 0 0 1 0 0 1 1. Sequence counter value decremented. Now check the sequence counter value. If it is 0, stop the procedure. Now sequence counter value is not equal to 0. So again we have to go back to comparison. So in the step 2 initial values are 1 1 0 0 1 0 0 1 1 3. Now second process is again we have to compare q and qn plus 1 value. So qn value is 1, qn plus 1 is also 1. So if both are 1 1, qn plus 1 are 1 1, both are 1 1, simply we are performing arithmetical shift right. Simply we perform arithmetical shift right. So whatever the accumulator value in the most significant bit, that can be write 2 times. So 1 1, and second value is moved to third position, third value is moved to fourth position, fourth position value is shifted to Q. So this value is 1, this value is 0, and this value is 0, and this one is moved to Qn plus 1. Next step is after shifting, right shifting, we have to decrement the Qn plus 1 value. Sorry, we have to decrement the sequence counter value. Second step is decrement sequence counter. So 1 1 1, sorry, 1 1 0, and this one is moved to here 0 1 0 0 1 3. So shifting, now check the shifting operation. So first a most significant bit value in the accumulator write twice. So 1 1, second position value is 1, third position value is 0, and last least significant bit in the accumulator is shifted to Q. So 0, and most significant bit in the Q is shifted to second position in the Q, that is 1 0 0. This one is moved to here. Next, decrementing the sequence counter value. So already sequence counter is 2 is there. So now we are decrementing sequence counter as 2. Minus 1, so we get 2. So it is also not equal to 0. Again we compare the qn plus 1 value. Again we have to compare qn plus 1 value. That is the step 3. In the step 3, initial values are 1 0 0 1 0 0 1. Sequence counter value is 2. Again compare qn plus 1 value. So again compare qn plus 1 value, q and qn plus 1 value. So q value is 0, qn plus 1 is 1. So 0 1. Now see the what is the operation we are performing is 0 1. For 0 1, we are adding accumulator value to B register. That means M value. So whatever the accumulator value, we have to add that value to M. So you see here, initially M we are taking as 0 1 1 1. Now we are add AC equal to AC plus M. So M is 0 triple 1, 0 1 0 0 1 2. Now add this value to accumulator. 0 plus 1 is 1, 1 plus 1 is 1 0, again 1 plus 1 plus 1 is 1, 1, sum is 1, carry is 1, again 1 plus 1 is sum is 0, carry is 1. If any carry is occurred in the accumulator, you have to ignore it. Now the values are 0 1 0 1, again 0 1 0 0, qn minus 1 is 1, sequence counter is 2. So what is the next step we have to perform here is arithmetical shift right. After performing sequence counter value in the accumulator value, so first operation is comparing, second operation we are adding the accumulator value with my m value, and next one is arithmetical shift right. We have to perform arithmetical shift right. So by performing shift right operation, we have to write most significant bit value in the accumulator as twice. 0 0, third value is 1 and fourth value is 0. This one is moved to qn value, q value, that means 1 0 1 0. This value is moved to here 0 and 2. Sequence counter value is 2. So third step is we are decrementing the sequence counter value. Decrement sequence counter value. Sequence counter. Already 2 is there. We are decrementing the sequence counter. We get 1. Okay. So here 1 is also not equal to 0. Again we have to perform next step. That is step 4. That means cycle 4 or step 4, whatever it may be. Step 4. Both are equivalent. 0 0 1 0. 1 0 1 0 0 1. Again we have to compare qn and qn plus 1, both are 0 0, both are equal. So first operation we have to perform is arithmetical shift right. So arithmetical shift right we are performing 0, third value 0 1, this value is moved to here 0 1 0 1, this value is 0 and sequence counter will be 1. After the second operation, arithmetical shift right operation, we have to decrement the sequence counter value. So sequence counter value is already 1 is there, we have to decrement it. So we get the 0. So it is equal to 0. So sequence counter is equal to 0. We are end the process. End the process. Now the product value contains accumulator and Q value. So product equal to AQ. So A value is 0001, Q value is 0101. Now you can check the value. So 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So first value is first position, second, fourth, 8, 16. So now we add the value 16 plus 4 plus 1. So we get 16 plus 4 plus 1, 21. 16 plus 4 is 20, 20 plus 1 is 21. So now observe the most significant bit value in the accumulator, that is 0. That indicates positive value. So we get the positive value. That means plus 7 into minus plus 3 equal to plus 21. That is the operation we performed in the Booth's multiplication algorithm. Thank you. So if you have any doubts, please ask me or comment in the comment section. Thank you.